The random rotations that we've added to the static portion of the building to add all of that interesting crack detail is really helping out a lot, but all of the floors of this building still look pretty straight. And if this building is getting destroyed as heavily as it is, then I'd expect all of those floors to sag down a little bit when all of these surrounding areas are destroyed. Now to sag those floors, I'm going to use the unfractured version of our interior geometry to design the shapes of that sagging. So if we go back to that week 2 prep building stage, and then you go to the area where you've set up your fixed interior geometry, we can object merge this into our post-sim setup. So I'll go back to my post-sim tweaks and add an object merge and point that to our out fixed interior. Next, I will isolate just the floor sections of that geometry. So I'll use a split and connect the object merge to that. And in that split group, I'll use the name is equal to star floor star, but not name is equal to the center. However, it looks like we're not having any of those center floor sections removed. So I'm just going to check the spreadsheet to see if that center is in the name, and it looks like it's not. And we should have set that up back in our fix interior portion of the prep. So if we go back to that fix interior and look at where we set up that center name prefix, we'll double check that spreadsheet. And sure enough, it looks like the name is set there, but when we unpack it after we set that center name prefix, we didn't transfer that attribute. So it's not inheriting that new name from those packed pieces. If we check this unpack node, you'll see none of those pieces have center and the name. And if we select name from these transfer attributes options here, then once we unpack it, all of those pieces will inherit that packed name, and now we have some of those pieces tagged as center floor. This isn't the most crucial thing. This sag floor setup will probably work fine if you don't remove that center floor section, but I just like keeping it as clean as possible and not including sections that I don't need. So I'll go back to my post-sim tweaks, and with that name fixed on all of those floor sections, you can see the center part is now removed in this split node. And I'll call this split floor, and then we're going to isolate just one bit of planar geometry for each of these pieces. Now with floor geometry, this is pretty easy because we can just use the normal direction to get a flat plane for each section. So if you drop in a delete and set the operation to expression, and then that expression is going to be at n.y is less than 0.5, and you'll see that isolates just the areas of our geometry with the normals pointing straight upwards. Now I'd also like to chop out just that simulation area that's getting destroyed, so I'll use a shrink wrap, and I'll connect that to our fractured geometry from over here, so that'll isolate roughly the area of destruction, and then I'm going to group the points within that shrink wrapped area. So I'll connect the delete to the first input, the shrink wrap to the second. I'll call that group sim area, set the group type to points, base group off, bounding regions on, and set it to bounding object. So now we're just grouping that area that we're interested in deforming, and I'm going to promote this to prims before I do the deletion. So drop in a group promote, set the convert to primitives, and in that drop down, it's kind of hard to find the group among all those names there. So I'm just going to type in sim area. And if you view that, you'll see that's promoting that up to primitives. Now I will isolate that area with blast, connect it to the group promote, and in that blast we'll select that sim area group and flip that to delete non-selected. And then we don't need this sim area group anymore, so I'm just going to drop in a group delete and select sim area from that drop down. Now I'll use an exploded view just for a moment to view all the different sections of this flat floor geometry. and we should give each of these an active frame to animate the amount of sag on the floors. Kind of similar to how we used an active frame to control all of those random rotations on the pieces for the crack detail in the last video. Now we want each section of this floor to have one active frame value determining when that sag is going to happen. We don't want the different points or prims to have individual active frame values. So I'm going to convert these to packed objects so that each of them are represented by one point and one primitive. You can use either the normal pack or an assemble node to convert that to packed geometry. I'm going to use an assemble in this case. And with the assemble SOP, you have to make sure that you turn on this create packed geometry option. And then we're going to copy over that active frame to these pieces of the floor. Now we've already set up an active frame value on the static sections of our geometry when we set up those random crack rotations, so we can just transfer that active frame value from here. However, before we do that transfer, I'm going to isolate just the floor section, so I'll copy our split that we used for the floor there. Then I'll connect it to our static geometry that has that active frame value. And then we'll do an attribute transfer onto those flat floor pieces. So those floor bits will go into the first input, and this fracture geometry with that active frame will go into the second. And in the attribute options here, I'll turn off primitives and select active frame from the drop down under points. And under the conditions, I'll turn off the distance threshold because we just want it to grab the nearest value regardless of distance. And now that each of these floor sections have an active frame, we can now unpack that back to regular geometry and make sure to select that active frame under the transfer attributes parameter. Now we're also going to need some more resolution on these flat planes, because if we want to sculpt a nice sagging shape, then just having a couple primitives spanning across that entire surface is not going to look very good. So I'll add a divide SOP. I'll set the maximum edges to 4 and turn on this bricker polygons option. And whenever I'm doing a bricker, I often like to copy that first size parameter and then paste the relative reference into Y and Z. And in this case, I'll just try a size of 0.3. So if you display that divide, that gives us a lot more resolution to work with when sculpting these sagging shapes. Now, in order to procedurally sculpt that shape, we need to know how far the points on the floor are from the nearest wall. So I'll make a split node to isolate that wall geometry. I'll call this split wall, and then I'll connect this up to the second output of the split where we isolated the floor geometry. So we've got the floor out the first input and the walls and center section out of the second, although we really just want the walls only, not this center bit. So in the split for the wall, I'll just say at name equals star wall star. Now I'm going to use a color attribute to determine how far these sections of the floor are from the nearest wall. So I'll drop in a color node on the floors and leave that at the default of white. And I'll create another color SOP for those walls, and I'll set that to red. Then I'll do an attribute transfer, connect the floors to the first input, walls to the second. We'll turn off the primitive attributes, and under points, we'll select that CD for the color. Now for this transfer, the distance controls are pretty important. I'll set that distance threshold to 0, but then turn that blend width up to 3, and you can see that creates a nice fall off from the walls to the middle of the floor. Now to create these sagging deformations, I'm going to use a point wrangle, and because I'm going to use some randomization based on the names of each of those sections of floor, and we're working in a point wrangle here, we need to promote the name attribute from prims to points. So I'll drop in that attribute promote, connect that up, and we'll set the original class to prims and select the name. Now I'll add the vex to apply the deformation, and we'll hit our little button here to create any of those reference channels within that vex code. In this case, I'm using a sag amount channel so that we have an overall multiplier on the amount of sagging that we're adding. To apply these sagging deformations, I'm first generating a random multiplier for each section of the floor. This is generating values from 0.3 to 1. If I change that 0.3 to just a 1, you can see all of these floors are sagging approximately the same amount. But when we vary that value from 0.3 to 1, that gives us a bit more variety in how much those are sagging down, and you can tweak that to your own artistic judgment. Then I'm generating an activate variable to blend in these deformations over the course of 10 frames based on each point's active frame attribute. And then to really apply these deformations, I'm just subtracting values from the Y position of each point. I'm multiplying that random multiplier times the activation, times that sag amount channel that we can slide here, and then finally multiplying in the green channel of the color so that we get the full deformation in the middle of the floor and no deformation near the walls. Now to keep things tidy, I'll select that section where we're generating these planar floor deformers and create a box around that. And then we can use these planar floor deformers to point deform the actual fractured floor geometry. So if we back up in our viewport and scrub through our timeline here, you can see those sag animations blending in over the course of the shot. And then I'm going to go to the output of our random rotations on the static portion of the building and split the floors away so that we can point deform them. So just add that split, set the group to name equals star floor star to isolate just that area. Then we can wire those floors into a point deform, and we'll take our attribute transfer on our planar deformers and add that to the point deform rest shape, and this sag deform wrangle into the deformed position of that point deform. And if you display that, you can see all of the fractured sections of our floors are sagging down once the nearby areas become active. Now, if you really want to get picky about exactly how this looks, you could control the rotations on the floors separate from the walls. And in my version of the shot, I added a primitive wrangle on these floors just before that point deform to blend out the rotations on the transform matrix for all of those pieces. Now don't worry if that's confusing, because it took me a while to understand transform matrices and how they work on packed objects and how to access those in Vex. And I have a library of snippets that I've come up with to handle these things, and I highly suggest that you save this one because this is a harder one to remember off the top of your head. And this is a totally optional step, but in this Vex example, I'm running over each of these packed primitives, and I'm grabbing that transform matrix and extracting just the rotation component, and then creating this rotation multiplier channel on the wrangle so that I can control how much of the rotation we have on all of our floor sections. So if I bypass that wrangle, you can see a bit more rotation on these pieces, and it turns it down a bit with that on. In my case, I set that multiplier down to 0.5. And if you display the point deformed version of these floors, then the usefulness of that becomes a little bit more apparent, because if we go to any of these sections where there's some clear sagging happening, if I disable that wrangle here, you can see that floor looks a bit messy. Maybe you prefer it, but I like seeing those floors a little bit more intact than that. And it probably doesn't make a big difference in the final shot, but this was just my personal preference. And before I wrap up this sag floor section, I'd like to make another little tweak to the attribute transfer from the wall onto the floor. Now, this kernel function defines how the attributes fall off with distance. With this default element model, this gives us kind of a sharp peak at that sag point, which I'm not a big fan of, but if you switch it to some of these other models, Some of them give you some better results. The blend model is kind of interesting, but it's a little bit flat on the bottom, and you can try out some of these other models, but the one that I liked for this was the Lynx. It seems to give us a nice gentle and realistic slope to that sagging shape. If we go down to where we're point deforming our floors, we can see what that looks like on the actual geometry. Now when applied to our fracture geometry, the effect is a bit more subtle as far as that difference between these different transfer models, but I still do like the Lynx more than the default Elent. And for some of these floors where it's perhaps a little bit more intact, it might be a little bit more obvious than some of these more destroyed floors. Like this one in particular will probably show it a little bit better than some of those lower floors. Now to finish up these modifications to that static portion of our building, we'll just merge these floors back with the walls. And to keep things nice and descriptive, I'll add a null at the very end here and call that animated static section. And finally, if we flipbook the results of all of our post-sim tweaks on that static section, you can see all of that floor sagging combined with those random crack rotations. And this might look a little bit artificial right now, but once this is layered in with the real RVD sim on top of it, this adds a real nice layer of deformation and interesting detail to the shot.